Hi, in this video we're going to look at properties of the definite integral and especially how that relates to the Riemann sum definition of the definite integral. Alright, so these are the types of questions I usually ask of Calculus 1 students to try to get at their understanding of that Riemann sum definition. So these would be good to remember and study for an exam. Alright, so for this one I've given you a specific function and a specific interval and asked some specific questions about it. So the first thing it asks you to do is to sketch the function and shade the region represented by this integral, and this is the generic form with just an f of x there. Since I have a specific f of x here, we can go ahead and replace that. So this question could be asked either way. It might just say to sketch the region represented by the definite integral given here, and you would recognize that it's that function on the interval 0 to 3. Alright, so let's go ahead and sketch that function. You should probably recognize that that equation is a parabola, and maybe if you rewrite the terms in the opposite order it's a little bit easier to think about the graph. So you can think about that as a parabola that has been flipped down, opens down, and the vertex is shifted up 2 units, so you have a vertex at y equals 2. So it's easy to sketch a rough sketch of that. I'm going to go ahead and plot a few points here, specifically on the interval 0 to 3. We're going to need a kind of accurate graph to answer some of the other questions here. The other point that might be relevant to pay attention to is the y-intercept. There's a y-intercept somewhere here between x equals 1 and x equals 2. Intermediate value theorem tells us that. So I could figure out that that is at y equals square root of 2 by plugging in 0 for y in the original function. Okay, so I went ahead and sketched both halves of the parabola here. I really only need the right half of the parabola, and it's asking me about the region represented by this definite integral. So it's the region between that function and the x-axis from x equals 0 to 3. So part of that region is below the x-axis down here. Part of that region is above the x-axis up here. And so when I think about evaluating that integral and think about that Riemann sum, know that we're going to get positive y coordinates. So this part will give us a positive value for that definite integral, and then I'll have a negative part over here. And so when I add all that up, I'm going to have some cancellation with positives and negatives, and then the question may be about which size is bigger, and so kind of which one wins. Does it add up to 0, or do we have more positive than negative, or what? So we'll talk about some more of that later. But for this one, this is all it asks us to do on part A here. Sketch the function and shade the region represented by that definite integral. Okay, there's some other parts here that ask you to do other things related to the definition. All right, part B says on the sketch above, we're going to partition that interval using this set of points. And so what it's given us here is the x coordinates that we're going to use to cut the interval 0 to 3 at. Okay, so I just drew marks on my interval at x equals 0, 1, 2.5, and 3. So the partition, the idea of the partition is that you're using it to cut the interval at those points. All right, the next thing it asks me to do here is find the norm of the partition. So that is that symbol that looks like a double absolute value bar around the P, the norm of the partition, and that is defined to be the width of the largest subinterval. Okay, so I'm going to just use some notation here. You might be able to just look at the graph and easily answer this question, but just to make sure that we're clear about what this is asking here. So I'm looking at all the different delta x's. My delta x1 is the width of the first subinterval. So the first interval that goes from x equals 0 to x equals 1, and the width there is 1 minus 0. And then the delta x2 is the width of the second subinterval. So that's the interval that goes from x equals 1 to x equals 2.5. So 2.5 minus 1, that's width 1.5. And then the delta x3 is the width of the third subinterval from x equals 2.5 to x equals 3, and so that one has width 0.5. So the largest delta xk is 1.5, so that's the norm of our partition for this partition. we eventually want to let the norm of that partition approach 0, but this partition we've started with has norm 1.5. All right, and then it asks us on the sketch above to use the left endpoints of each of those subintervals to draw the rectangles in the Riemann sum. All right, so I'm going to make a little table of values here. We already have some of these from our earlier table, but I'm using the cut points from the partition. And because it told us to use the left endpoints of each subinterval, if you can't see it from looking at this list, you can see it from looking at the graph. If I'm using the left endpoint of each subinterval, on that last subinterval, I'll be using 2.5, and then that's the last subinterval. So I don't really need the one at x equals 3. So really I just need these 3 values here. All right, so I'm going to use those x equals 0, 1, 2.5 to draw my rectangles here. So for this first one, I've got my left endpoint at x equals 0. I plug that into the function and I get 2. That gives me the height of my first rectangle. So the first rectangle here is width 1 and height 2. And it's using a y equals 2 for its height, and that's at x equals 0, the left endpoint of that subinterval. All right, the next subinterval, the left endpoint is at x equals 1, and the y-coordinate there at x equals 1 is y equals 1, and so that's the height of this next rectangle, 1. So it's 1.5 units wide and 1 unit tall. All right, and then the next subinterval is using x equals 2.5, and the y-coordinate at x equals 2.5 is negative 4.25. So for that one, I have a rectangle that goes down below the x-axis here. Right, and I could actually calculate this sum, right? I could take the width times the y-coordinate for each rectangle. For this question, though, it's really not asking you to calculate things, it's asking you to sketch things. So those 3 rectangles are the Riemann sum with that specific partition and left endpoints. All right, and then the last thing it asks us to do here is to write the limit of the Riemann sum that's used to define this definite integral. So all of the parts before this were for a specific partition and a specific choice of how we're going to do those rectangles, but this part is asking us for the general definition. All right, so the definite integral that I'm defining is from 0 to 3 of the function we're working with, 2 minus x squared dx. So that is the definite integral, and that is defined to be a limit of a Riemann sum. I'm going to come back here and fill in the limit in a second here. So I know it's the first thing you write when you write from left to right, but when you think about mathematically what's happening here, really there are several parts that happen first. All right, so I have a function, 2 minus x squared. In that definition of that Riemann sum, we choose a point in each subinterval that we're using to draw the rectangles. And so those are the C values in that definition. I didn't write those down up here, but when we talked about that Riemann sum definition, you choose a point in each subinterval, you plug that in to get your height. And so we use C sub k for that. So in this general definition, I'm going to have my function 2 minus x squared, but what I'm putting into the function is the C sub k's that are chosen. So this is my function with the chosen x equals C sub k plugged in. All right, so I have the y-coordinate, and then I'm going to take that times the width of the subintervals, and they may or may not be the same width for each subinterval. So what I've got here, when I think about these two parts times each other, I've got a y value times a width. And so that gives you a signed area of a rectangle. It's not technically an area because this y value could be negative. And then for the Riemann sum, I add them all up over however many there are. In our example, there were 3, but in general, you want to let there be n, and you eventually want that n to approach infinity, and you want the width to approach 0. Letting n approach infinity is not enough. That won't force all the widths to be 0 because it's easy to think about. If you think about chopping an interval up, I could make infinitely many cuts right here and still have infinitely many pieces, but unless I force the widths to all be 0, I still have a great big rectangle on one piece that's not going to really accurately measure that area. So I want both of these things to happen. The way we define the Riemann sum, when you let the norm of the partition approach 0, that forces the number of rectangles to approach infinity. It is not necessarily true that the other way around works. All right, so I want the limit as the norm of the partition approaches 0. I wrote that in blue there. Sometimes I see students write n approaches infinity there. You want that to happen, but that doesn't force them to be narrow. That only forces infinitely many, and you need both things to happen. All right, so if you are just taking this class, sometimes it is easy to sort of look at what's given and figure out you need to write this here and write that there and not really maybe entirely understand what you're writing, but still be able to get the answer correct. If you are going on in calculus, it is important that you also try to understand this and understand some of the comments that I've written below here. What this represents, that's that function with the chosen x equals c sub k plugged in. What it represents when you plug that thing into the function, that you get an output value for the function. What the delta x's at the end of this Riemann sum represent, that those are width or size of the little pieces in the partition, that you add all those things up, that definite integrals are really sums, and that there's some limit involved, and what exactly is happening when that limit happens. Really, there are two things happening, even though you only have one thing written down there. One thing forces the other thing to happen. So especially if you're going on and taking more math, more calculus after this, really try to make sure that you understand what you're writing down for that Riemann sum.